Atomic layer deposition. Atomic layer deposition, or ALD, is a cutting-edge precision thin film technology that enables the construction of materials at the atomic scale. By depositing materials one atomic layer at a time, ALD delivers unmatched control and precision in film thickness, composition, and uniformity. This technique is foundational in nanotechnology and is critical in fabricating advanced semiconductor devices. ALD excels in three key areas: atomic scale accuracy, layer-by-layer control, and precision technology. First, its atomic scale nature means we can manipulate materials with near-molecular precision, enabling devices to shrink further while improving performance. Second, its layer control allows for uniform coatings even on complex 3D structures, which is crucial for modern chip architectures. Finally, ALD represents the pinnacle of precision tech, enabling reliable, repeatable, and scalable deposition processes. ALD is a cornerstone of next-generation electronics and advanced material engineering. What is atomic layer deposition? Atomic layer deposition, or ALD, is defined as a thin film deposition technique that creates materials by depositing one atomic layer at a time. This level of precision is possible through self-limiting chemical reactions. These reactions stop automatically after completing a single atomic layer, ensuring high uniformity and eliminating overdeposition. The key to ALD lies in its ability to build up layers in a strictly controlled sequence, each step preparing the surface for the next. This enables the creation of films with exact thickness, excellent conformality, and exceptional repeatability. The process is not only reliable, but also highly scalable, making it ideal for advanced semiconductor manufacturing. The core concept of ALD is simple yet powerful. One atom at a time results in one perfectly controlled layer. This layer-by-layer growth model enables engineers to fine-tune material properties at the nanometer scale, critical for next-generation technologies. What is atomic layer deposition? Atomic layer deposition offers several unique advantages that make it one of the most precise thin-film deposition techniques available today. First, ALD delivers angstrom-level precision, enabling control of film thickness down to individual atomic layers. This level of accuracy is critical in applications where even a fraction of a nanometer matters, such as semiconductor devices and advanced sensors. Second, ALD provides uniform coverage. It can coat even the most complex 3D structures, including deep trenches and high aspect ratio features, with consistent thickness. Third, ALD is a low-temperature process, which means it can be used on temperature-sensitive substrates and materials without causing thermal damage. Finally, ALD is self-limiting by nature. Each reaction cycle automatically stops when a single atomic layer has formed, preventing overdeposition and ensuring repeatability. These four characteristics, precision, uniformity, low thermal impact, and self-limiting behavior, make ALD ideal for next-generation nanomanufacturing. The ALD process. The atomic layer deposition process is a four-step cyclic deposition technique that builds one atomic layer per cycle. It begins with precursor adsorption, where reactant A chemically attaches to available sites on the surface. This step is self-limiting, meaning it stops once the surface is fully saturated. Next comes the first purge, which removes any unreacted precursor and gaseous byproducts from the chamber to prevent unwanted reactions. The third step is co-reactant exposure, where reactant B is introduced and reacts only with the surface-bound layer from step 1, forming a uniform thin film. Then, a second purge cleans the chamber of excess reactants and reaction products, preparing it for the next cycle. This process is highly repeatable, offering atomic-level precision, uniform thickness, excellent conformality, and low-temperature operation. Each cycle adds one atomic layer, ensuring precise layer control essential for advanced semiconductor and nanotechnology applications. Key advantages of ALD. Atomic layer deposition offers several revolutionary advantages in thin film technology, making it a critical enabler in advanced manufacturing. The first key advantage is atomic precision. ALD enables thickness control down to plus or minus 0.1 angstroms, which is sub-nanometer accuracy. This is achieved through self-limiting reactions that allow only one atomic layer to form per cycle. Such precision is essential for scaling semiconductor devices and creating uniform nanoscale films. The second advantage is perfect conformality. ALD can coat complex 3D shapes, including high aspect ratio trenches and deep vias, with 100% uniformity. This makes it especially useful in advanced node transistor fabrication and 3D nanostructures. The third benefit is low temperature processing, typically ranging from 50 to 300 degrees Celsius. This gentle approach preserves thermally sensitive substrates and reduces thermal stress, making ALD suitable for flexible electronics, photonics, and other temperature-sensitive applications. Together, these features make ALD an indispensable tool in nanotechnology and precision engineering. Key advantages of ALD. Atomic layer deposition, or ALD, offers transformative benefits in thin film technology, making it a vital process in semiconductor manufacturing. One major advantage is its ability to deliver uniform thickness, maintaining plus 2% variation across the entire wafer. This level of precision is crucial for device performance and yield. Next, ALD provides material flexibility, supporting over 100 different materials including metals, oxides, nitrides, and sulfides. This versatility allows for a wide range of applications from advanced logic to memory devices. Another key benefit is excellent step coverage. ALD achieves near 100% conformality, even over complex topographies and high aspect ratio structures, ensuring complete and defect-free coverage. Finally, ALD is highly repeatable. Its self-limiting surface reactions ensure consistent results batch after batch. In essence, ALD enables atomic-scale precision manufacturing, unlocking new innovations in nanotechnology and pushing the boundaries of device scaling. Applications of ALD. Atomic layer deposition is revolutionizing multiple industries by delivering nanometer scale control and ultra-thin films with exceptional uniformity. In the semiconductor industry, which represents a $15 billion market, ALD is essential for fabricating advanced devices. It's used in gate dielectrics to create highly reliable transistors, in memory devices to ensure precise layer deposition, and in logic circuits where uniformity at nanoscale dimensions is vital. Moving to solar energy, ALD contributes to achieving 25% efficiency by enhancing the performance of transparent electrodes, improving passivation layers that reduce surface recombination, and forming buffer layers for better material interfaces. Lastly, in energy storage, ALD is enabling batteries with up to 3 times the capacity. It achieves this through high-performance electrode coatings, solid electrolytes for safety and efficiency, and protection layers that prevent degradation. Altogether, ALD is powering innovation from chips to clean energy. Applications of ALD. Atomic layer deposition continues to expand into new markets, offering atomic precision that enhances both performance and reliability. In displays such as OLED and LED technologies, ALD provides critical barrier films that protect sensitive layers from moisture and oxygen. It's also used for encapsulation, which extends device lifespan, and in creating touch sensors that require ultra-thin, uniform coatings. In the medical field, ALD ensures biocompatibility for implant coatings, supporting long-term stability inside the body. It also aids in controlled drug delivery systems and enables highly sensitive biosensors for diagnostics. In catalysis, ALD boosts activity and efficiency by enabling precise coatings on fuel cells and nanoparticles, and by modifying support materials for optimized chemical reactions. With 100+ materials available, a projected $5.8 billion market by 2028, and 15% annual growth, ALD remains a high-impact solution, especially with semiconductors accounting for 67% of current applications. Types of ALD. Atomic layer deposition can be implemented through two primary approaches: thermal ALD and plasma-enhanced ALD, each offering unique advantages based on process needs. Thermal ALD is a heat-driven process operating within a temperature range of 50 to 400 degrees Celsius. While it typically has slower deposition rates, it delivers excellent conformality, making it ideal for precise and uniform coatings. Thermal ALD is best suited for gate dielectrics, passivation layers, and barrier coatings where temperature tolerance is not a constraint. On the other hand, plasma-enhanced ALD, or peeled, utilizes plasma to enhance surface reactivity. This approach enables lower temperature processing, typically between 25 to 300 degrees Celsius, which is critical for temperature-sensitive substrates. Peeled offers faster deposition rates and increased reactivity, making it a strong choice for memory devices and high-throughput production environments. Choosing the right ALD type depends on substrate sensitivity, desired film properties, and manufacturing throughput goals. Types of ALD comparison. To choose the right atomic layer deposition approach, it's helpful to compare the characteristics of thermal ALD and plasma-enhanced ALD across key parameters. Starting with temperature range, thermal ALD operates between 50 to 400 degrees Celsius, while plasma-enhanced ALD enables lower temperature processing from 25 to 300 degrees Celsius, making it more suitable for heat-sensitive materials. In terms of deposition rate, thermal ALD typically achieves 0.5 to 2 angstroms per cycle, whereas peeled can reach 1 to 3 angstroms per cycle, offering faster processing times. For conformality, thermal ALD generally delivers excellent results, ideal for coating complex topographies, while peeled provides good conformality, slightly less ideal for ultra-high aspect ratio features. Finally, when considering equipment cost, thermal ALD is more economical, whereas peeled involves higher equipment costs due to plasma integration. In summary, thermal ALD is preferred for gentle, conformal coatings, while peeled is better suited for faster throughput and temperature-sensitive applications. ALD equipment and technology. Atomic layer deposition, or ALD, relies on a system of tightly integrated components to deliver precise thin film coatings. At the heart of the system is the reaction chamber, where sequential surface reactions occur. Precursor A and precursor B are introduced in alternating pulses. Each precursor reacts only with the surface, ensuring atomic level control. The vacuum pump maintains low pressure, critical for removing excess gases and byproducts. The heater control regulates chamber temperature, allowing deposition within a wide range, from 25 degrees Celsius up to 500 degrees Celsius. The control system is key for managing process parameters: chamber pressure, gas flow, vacuum integrity, and operational safety. With 8 to 16 precursor lines available, the system offers flexibility for complex processes. Base pressures can reach as low as 10 to 6 torr, ensuring a clean environment. Ultimately, ALD systems achieve high uniformity, within plus or minus 2%, and a process yield reliability of 99.8%. ALD equipment categories. Research and production systems. Atomic layer deposition systems are available in two major categories: research systems and production systems. Research systems typically range in cost from $100,000 to $500,000 and are designed for small substrates up to 4 inches. These systems support multiple precursors, enabling researchers to explore various chemistries and film stacks. They provide flexibility for experimental process development and are often equipped with in-situ monitoring tools for real-time feedback. On the other hand, production systems are engineered for large wafer handling, supporting sizes between 8 to 12 inches. These tools are priced between $1 million and $5 million and are built for high-throughput automation. They feature advanced process control systems and are capable of continuous 24/7 operation. Modern ALD equipment combines precise engineering with smart automation, achieving sub-angstrom thickness control of plus or minus 0.5 angstroms, reproducibility as high as 99.9%, and compatibility with extreme aspect ratios up to 10 to the power of 9. Challenges and limitations. Atomic layer deposition provides unmatched precision, but it comes with critical limitations that must be understood. The primary challenge is slow deposition rates, only about 0.5 to 2 angstroms per cycle. To deposit a 10 nanometer film, it can take several hours, whereas other methods like chemical vapor deposition complete similar tasks in just minutes. For a 50 nanometer layer, ALD may require between 500 to 1,000 cycles, translating to 8 to 12 hours of typical cycle time. This results in low throughput, making ALD less ideal for high-volume manufacturing without optimization. Another major limitation is cost. Equipment alone can exceed $1 million, and operational costs are high. Each wafer may cost more than $500 due to expensive precursors and the need for 24/7 system operation. These constraints, speed, cost, complexity, and material limitations, are reflected in the challenge impact chart, highlighting how each factor affects overall scalability and adoption. Process complexity and key limitations. Despite its precision, atomic layer deposition faces significant technical complexity. One key challenge is the limited precursor library. Only certain materials are compatible with self-limiting surface reactions. Temperature constraints also limit flexibility. Some processes require very specific thermal windows. Process optimization is complex and time-consuming, especially when balancing uniformity, throughput, and material performance. Surface chemistry and nucleation control add further layers of difficulty. Even after development, scaling up from lab to fab introduces new issues. What works in research may not translate efficiently to high-volume production. Compared to CVD and PVD, ALD has slower speed, higher cost, and greater complexity, as shown in the process comparison chart. Limitations include long cycle times, high capital investments, limited material options, and scale-up difficulties. Nevertheless, ALD remains critical for applications under 10 nanometers, with growing market demand and ongoing improvements in equipment and process design driving its future potential. Future outlook and summary. Atomic layer deposition is poised for strong market growth, with projections estimating the market to reach $4.8 billion by 2030. This forecast reflects a compound annual growth rate of 15.2% from 2024 to 2030. Over 50 new application areas are expected to emerge, driven by rapid advances in semiconductor manufacturing, increasing demand for AI hardware, and the evolution of quantum computing. Key takeaways include ALD's unmatched atomic precision, which enables precise layer control at the sub-nanometer scale. Another major advantage is 3D conformality. ALD excels at coding high aspect ratio and complex geometries, critical for modern chip designs. ALD is especially important for nodes at 5 nanometers and beyond, making it essential for future logic and memory technologies. While speed challenges remain, they open the door for innovation in high-throughput ALD solutions. With a growing number of applications, ALD continues to expand its footprint across the semiconductor industry and beyond. Future outlook and summary. Atomic layer deposition, or ALD, is poised to shape the future of nanotechnology and advanced semiconductor manufacturing. The central idea is clear: the future is atomic. As technology trends push toward ever smaller features and greater functionality, ALD is uniquely positioned to deliver precision at the atomic scale. Its power lies in innovation, an engine that never stops. With continuous improvements in precursor chemistry, process control, and reactor design, ALD is enabling the development of new device architectures and material systems that were previously impossible. Its global impact is profound. From enabling next-gen computing and memory to driving clean energy and biomedical devices, ALD is a transformative force across industries. And finally, the possibilities are unlimited. As the boundaries of science expand, ALD stands ready to meet future demands, layer by layer, atom by atom.